The last topic we're going to look at for GCSE to A-level physics transition is errors and uncertainties. Now, you already met some idea of errors in your GCSE. You met systematic and random errors, for example, and you would probably have had to estimate errors as well. So this is a bit of a reminder of that, because often those topics get skipped, but also it's going to help you with a little bit of a primer of how to handle errors. There's a lot here we can't go into, but it's going to be a good start for you by way of transition. So first of all, a little bit of terminology for you. Errors. It does not mean mistakes. There's no human error. There's no mistake here. The word error, it means that there is a difference between what's measured and what's the accepted value of some quantity, which some exam boards call the true value. For example, you measure the charge of the electron, and you measure it to be slightly different from what the rest of the scientific community says, then you have an error associated with your answer. And errors are inevitable. You're always going to get errors with measurements. You can quantify errors by giving uncertainties as a way of sort of quantifying your doubt in a particular value. So uncertainties have numbers with them. So I'll often use the term errors and uncertainties interchangeably. They are actually slightly different in meaning. It doesn't really matter. Uncertainty gives you a range. That's what the numbers are. It's a range of values where your value is within that range, and you kind of hope that the accepted value is also within that range. So it is tied quite closely to the idea of accuracy, how close your range of measured values are to the accepted value. It's not very accurate measurement if the accepted value lies outside your uncertainties. And precision. So precision is how close together your values are. Whether they're close to the accepted value or not is irrelevant. For precision, it's just how close together your values are. So accuracy, we have random errors, which cause a bit of spread. And you've also got systematic errors. We'll talk about what that means in a second. Precision is only to do with random errors, not systematic errors. So random errors, you're always going to get them with every measurement you take. Small variations in, let's say, for example, machine tolerances. You're building a particular, I don't know what it is, shelf, and you cut a piece of wood to a certain size, but there's always going to be small differences, and if you were to very carefully measure the length of your shelf in different places, it'll actually be slightly different lengths. Very, very tiny differences. Tolerance in your ability to cut things to the same length, and that's going to give you random errors when you come to measure that length later. So there's no direction to it. Measurements can be slightly higher, slightly lower than whatever an accepted value would be. Systematic errors have a direction to them, a statistical bias to them. So for example, if my balance that I'm measuring a mass on, it was broken somehow, perhaps it was calibrated incorrectly. So for every kilogram that I put on top of this balance, it tells me 1.5 kilograms. And if I put 2 kilograms on, it tells me 3 kilograms. Well, that's a certain amount. In this case, it's a certain proportion different from the accepted value of the mass that I'm measuring. And therefore, that is a systematic error. Or it could be that the scale's all shifted. So my balance, when there's nothing on it, say 0.5 kilograms, I place a kilogram on it, it says 1.5. I place 2 kilograms on it, it says 2.5. So the amount that it is wrong by is the same amount each time. So that would be a systematic error. Sorry, a systematic error. Random errors tend to be distributed like this. This is a normal distribution or a Gaussian distribution. If you haven't studied much statistics, the numbers on the x-axis aren't going to make tremendous amounts of sense to you. That's sigma there, which is one standard deviation. And so this is one standard deviation from the mean, this is 2 standard deviations from the mean, and so on. and on the y-axis is your probability of measuring that particular value. So the likelihood of measuring a value that's very close to the mean should be higher than the likelihood of measuring a value very far away from the mean. It should be. That's what we would expect a spread of measurements to be like. What is standard deviation? Well, you can think about it as the mean distance from the mean. It's a nice way of thinking about it, but we're not going to cover that in this video because we're only giving you an overview. So random errors do tend to be normally distributed, and you can simplify the calculation of them. Rather than expressing those random errors in terms of standard deviations, which you can do in statistics, and we do it in physics, in A-level physics, to keep it simpler, we use the same approximation as you used in your GCSE. So in your GCSE, you use this approximation. If you have a range of values, then you take your maximum value, the minimum value, calculate the difference between them, divide it by 2. Half the range would be your absolute uncertainty. Now, a little thing about that, these values have to be values of the same measurement or the same data point. You can't calculate uncertainties where there's a list. So, for example, if I am measuring different diameters of a wire, and it's the same wire, and I'm measuring different diameters at different points along the wire, and I expect it all to be the same, but I might get slightly different values. I can use this approach to measure the uncertainty in those values. On the other hand, if I'm doing an experiment where I'm dropping something, maybe I'm timing how long it takes to fall, and as it falls, I'm dropping it from different heights each time, so I expect it to take more time to fall each time. On my table of results, I'm going to have a whole bunch of different heights, starting from low heights, going up to higher heights. I can't use this on that list to get an uncertainty in the height. That wouldn't make any sense, to get the maximum height I dropped it from and the minimum height I dropped it from. That's not what this is about. This is about uncertainties for a particular measurement that you will have repeated. Hopefully you'll have repeated it, but it's one particular quantity that we are measuring. So here is the example I gave of the diameter of a wire. You make multiple measurements in different orientations in different places, and you get perhaps 7 measurements, as you can see here. Well, the highest one was 1.03 millimeters, and the lowest one was 1.00 millimeters. So half of that range is 0.015 millimeters. That is your random error. That's your uncertainty presented as an absolute uncertainty in these values. You can't do it in this case. For example, if we're measuring the resistance of a wire as we change the wire's length, we can't just do 100 subtract 20 divided by 2 to get the uncertainty in the wire length. That doesn't work. That's not what we are doing here. So we do have to be a bit careful. Each of these rows is a data point. And if we had made multiple measurements of resistance for a particular wire length, then we could have an uncertainty for that particular resistance. But because we changed the wire length each time and only have one value of resistance for each, we can't really do very much with that. But we can estimate an uncertainty based on the instruments that we have used to measure. So, for example, if I used a ruler to measure the wire length, and in this ruler it could only measure to the nearest centimetre, and I used a resistance meter, an ohm meter, to measure the resistance that could only measure to the nearest 0.01 ohms. And I've got these data here. Well, what I can do with this is I can estimate the uncertainty, and it's going to be based on the resolution of the instrument. Now, if I've got multiple measurements of the same data point, then I can do half the range. That's fine. But if I don't, and I still need to estimate the uncertainty, then I can do this. I know that this ruler could measure to the nearest centimetre. So that 100 centimetres data point here, that could be as low as 99.5 centimetres, or it could be as high as 100.5 centimetres. So that's a range from 0.5 centimetres below the 100 to 0.5 centimetres above the 100. But when I make a measurement, I'm also holding the ruler against two ends of that ruler, of that wire length, the ruler against both ends. So there's going to be about 0.5 centimetre of uncertainty for each end, so that's combined to give me 1 centimetre of uncertainty. Now this is the case for all, I'm going to say all, possibly most, but certainly a lot of the analog instruments that we use to measure, is the uncertainty will be equal to the resolution of the instrument. Now with digital meters, digital instruments, it's possible to set the zero. You set that so there's no uncertainty on it. And so because you can set what zero is, then the uncertainty in that measurement is only going to be based on one reading, not the zero reading. And so, as you can see here, although the resolution of this resistance meter was 0.01, half of that resolution is what the uncertainty is in the resistance measurement, because in each of these resistance measurements, because I was using a digital meter. So if we're using an analog meter, then its uncertainty is equal to the resolution. If you're using a digital meter, then usually, because you can set the zero on it, it's going to be equal to half of the resolution. But you do have to use some intelligence when you're calculating these things. Okay, so that's just a summary of what I've just said there. You can read that yourself if you want to pause it and go ahead and read it. So I keep using the word absolute uncertainty. And what do I mean by that? Well, these are different ways of presenting uncertainties. We've got random error and we've got systematic error, but the uncertainty, remember how we're quantifying our doubt in a particular measurement, there's two ways of presenting that. We could present that as an absolute, which has units. So for example, 10 centimeters plus or minus 1 centimeter, that is an absolute uncertainty. Or we could present them as relative or percentage uncertainties. And I use the same symbols for these. That is a Greek letter epsilon. So for absolute uncertainties, we use a delta. For relative uncertainties or percentage uncertainties, we use an epsilon. And the only difference is relative uncertainty is presented as a unitless decimal, and percentage uncertainties, they are presented as a percentage, remembering that the percentage sign just means divided by 100. So if you multiply a relative uncertainty by 100%, you're multiplying it by 1, but it means that we can express it as a percentage. So that's how we calculate them. And we can come to that in an example in just a little bit. But the point is, because relative uncertainties and percentage uncertainties don't have units, the percentage sign isn't a unit, we can deal with them in the same way. So they're pretty much interchangeable. If you want to calculate a percentage uncertainty, you just times your relative uncertainty by 100%. Then the percent sign hangs around and gives you your percentage. Now, this calculation, the absolute uncertainty we already know about. That's half the range. That's fine. This value in the triangular brackets is what we call the mean value. Now, if you only have one value, one measurement, and you've estimated an absolute uncertainty based on the resolution of the instrument, well, in that case, your mean value is just the value that you've measured. But if you have a range of values, like our diameter of the wire example before, then your mean value is going to be adding up all of those values and dividing by how many you've got, the usual way of calculating mean. So to calculate the relative uncertainty, we just do the absolute uncertainty and divide it by the mean. Percentage uncertainty, just as it says here. Now, this is the key idea, and you've really got to be clear about this. When you are combining uncertainties, whether we add the absolute uncertainties or whether we add the relative or percentage uncertainties, it depends on what we're doing with the quantities. If I'm adding two lengths together and I want to know what the uncertainty is in the combined length, well, because I'm adding the quantities, then I add the absolute uncertainties. or if I'm subtracting one time away from another. Because I'm subtracting two quantities with units, then the absolute uncertainties can be added together, not subtracted, added together. Whereas if I'm multiplying or dividing two quantities together, like f equals ma, I've got uncertainty in m and uncertainty in a, and I'm timesing them together, I can't add the absolute uncertainties together because that doesn't work. Because the absolute uncertainty in the mass will have units of kilograms, and the absolute uncertainty in acceleration will have units of meters per square second. And you can't add kilograms to meters per square second. We talked about that in the dimensional analysis section. So we have to add together the relative or percentage uncertainties because they are dimensionless and they have no units. So let's look at an example. Here's two lengths, two wooden beams, and we want to add the lengths together for whatever reason. Well, we're going to measure the lengths of the beams, and that's easy enough. We just put them against some rulers and you measure them. And the top one looks like it's about 7.5 centimeters, and the one beneath that about 13 centimeters. And you add them together and you get 20.5 centimeters, and everyone's happy. However, that was okay at GCSE level. Let's look a bit closer. And for each measurement, for both of those lengths, there was 0.5 millimeter of uncertainty about this position. As long as the edge of this wooden beam was closer to 0 than it was a millimeter before or a millimeter after, then we call that 0. And we can't assume it's dead on 0. We just can't do that. So that is a reading of 0 plus or minus 0.5 millimeter. That's what that is. You can't say anything other than that. On the other side, let's just take the beam that was about 7.5 centimeters long. That was 7.5 centimeters, give or take 0.5 millimeter. That's what it's got to be. So if I had the longer one, that would be 13 centimeters, but give or take 0.5 millimeter. And I'm being consistent with my units here by giving centimeters as the unit for the uncertainty, but converting centimeters and millimeters is not too tricky. So because we've got two readings for each length measurement, the 0 reading and the reading at the other end of the beam, then we have to add together the uncertainties in those two readings, the absolute uncertainties in those two readings, because they're both lengths. And we get 1 millimeter of uncertainty. But that's 1 millimeter for each beam. So because we're adding together the lengths of the two beams, we also have to add the uncertainties together. The shorter beam was presented like this, the longer beam presented like this, and this symbol here is the plus or minus symbol. You might be familiar with that from square roots. Square roots have two possible values. It could be positive or negative a square root. But there we go. So, because if you square a number that's negative, you'll get the same thing as if you square the same magnitude number that's positive. So plus or minuses you'll be familiar with. The combined length is easy. We just add the means together, 7.5 plus 13.0. But the combined uncertainty, we add these two absolute uncertainties together. So our final length measurement we would express as 20.5 plus or minus 0.2. Actually, we wouldn't. We'd give our uncertainty to two significant figures, and that's not normal. That's not something that happens in the real world of physics. That's what happens in the little walled garden of A-level physics. In the real world of physics, one significant figure uncertainties are perfectly fine, but let's go with two significant figure uncertainties. But we'll talk about that a little bit later. This is an example of wave speed calculation. So in wave speed, we're multiplying together frequency and wavelength. And let us suppose that I've got the wavelength and the frequency expressed like this with absolute uncertainties. And we're asked, what does the wave speed equal? Well, I can easily calculate the wave speed mean just by taking the mean wavelength, that's 0.770 meters, and multiplying it by the wave frequency, that's 440 hertz. When I do that, I get 338.8 meters per second. Okay, fine. But now I've got to combine the uncertainties. And the problem here is that the uncertainties are absolute uncertainties, which means I've got to convert them first into relative or percentage uncertainties. The quantities are multiplied or divided. That's the first step. That's what we have to do. So to calculate the percentage or relative uncertainty, we do the absolute uncertainty divided by the mean for each of these quantities. Epsilon lambda means the relative uncertainty in lambda. Epsilon f means the relative uncertainty in f. There they are, and I've just converted them into percentages there just in case you found that easier to work in. Now, because we've multiplied or divided two quantities, in this case we've multiplied them, we add together the relative, or in this case percentage, uncertainties. So the percentage uncertainty of the wave speed is 8.76%. Now I could present the uncertainty like this. I could say the wave speed is 338.8 meters per second plus or minus 8.76%. But then again, remember we want two significant figure uncertainties, so I could write it like this instead. But usually we'd want to give our uncertainty as an absolute, not as a relative or percentage uncertainty, if it's the final answer. Not always, but usually. That's what we'd be more interested in. So here's our absolute uncertainty in C. What we've done is the conversion that we had before to calculate the relative uncertainty, we've simply rearranged that, algebraically rearranged that. So the relative uncertainty multiplied by the wave speed, the mean wave speed, which is this multiplied by that, is going to give us the absolute uncertainty in wave speed, 29.7 meters per second. Notice I'm using unrounded values and rounding afterwards. Now, look at this interesting step here. I've taken my uncertainty, my absolute uncertainty, 29.7 meters per second, and I've rounded it to two significant figures, as I said we would, but I've also rounded away the decimal place. And that's important. We do want the answer to be presented to the same number of decimal places as the uncertainty. And if you're writing it in standard form, that's easy to visualize. You want the same number of decimal places. That's important. It's a convention, really. There's no point having more detail here at all when this uncertainty is 30. What's the point of the 0.8 at the end? There's no point. It's unnecessarily detailed. Okay, so just some things to remember. Just a reminder, very important, adding quantities or subtracting quantities, it's the absolute uncertainties we add. We never subtract them. Multiply or divide quantities, then we add the relative or the percentage uncertainties. We never subtract them. If you're squaring a number, you're timesing it by itself, so you just add two lots of that relative uncertainty. And if you're raising something to the power of 3, you add 3 lots of that relative uncertainty. In fact, if you raise any quantity to a power, to the power of n, then you multiply the relative uncertainty by n. So square roots actually make the uncertainty go down, because you halve the uncertainty, the relative uncertainty, when you've got square roots. But unfortunately, we might have really complicated formulae where we have to convert multiple times. So let's look at an example. I think I already said this bit, didn't I? This was from before. Presenting uncertainties, two significant figures. Yeah, I've covered that bit. So let's have a look at a more complicated example. Let's use SUVAT. So here we've got an equation, v equals u squared plus 2as, all under the square root, or all to the power of a half. And let's suppose we want to calculate v, and we are told u, a, and s with absolute uncertainties. And you can see I've picked some numbers there. Well, we can calculate the mean v pretty easily, just by taking these values and plugging them into the equation. So, instead of u, it's 10.00, we square it. Instead of a, it's negative 9.81. Instead of s, it's 1.250. Notice that I use all of the decimal places. I'm not doing any rounding when I substitute, because I need to see clearly where these data have come from. And I get my value. Okay, fine. GCSE level, that would be okay. A level, if we're given uncertainties, we better use them. So let's go ahead and use those uncertainties. Now I'm just going to push all that up into the corner because I'm going to need quite a bit of paper for this. So you might have to zoom in to see this. That's the calculation we've already done. So the first thing I'm going to do is calculate the percentage uncertainties in my quantities. So there's the percentage uncertainty in our U. And it's the usual way of doing it. Mean value divided by, the absolute uncertainty divided by the mean value. And I could do the relative uncertainty in A, and I could do the relative uncertainty in S. And I've calculated those as percentage uncertainties as well. Now what we can't do is just add them all together. That would not be correct. That wouldn't be correct at all, because if you look at the equation, the U is being squared, and then it's being added to 2as, and the uncertainty in the number 2 is 0. There is no uncertainty in the number 2. We know for certain that 2 is 2. So what we're doing is we're multiplying a by s. So we can say that the percentage uncertainty in 2as is going to be the percentage uncertainty in 2, which is 0, plus the percentage uncertainty in A, which we've just calculated here, and plus the percentage uncertainty in S. So we now have the percentage uncertainty in 2as. Well, that's fine, but 2as is being added to u squared in this equation. So I'm going to have to know what the absolute uncertainty in 2as is. So we do the conversion. There's 2as, that's 2 times a times s. I haven't bothered with the negative sign because it's an uncertainty and they're always going to be plus or minus anyway. So I'm not going to bother with the negative sign. So I've just done 2 times 9.81 times 1.250 and then multiplied it by the percentage uncertainty in 2as, and there's the answer. Notice it has a unit. That is the unit of 2as. Now I'm going to want to add that to the absolute uncertainty in u squared. Well, first of all, I'm going to have to work out what the percentage uncertainty in u squared is. And that's going to be the percentage uncertainty in u plus the percentage uncertainty in u. Well, I've got the percentage uncertainty in u. I've already calculated that. That was 2.5. 2.5%. So I'm doubling it. I'm doubling 2.5%. Remember, if I've got something raised to a power, I can multiply the percentage uncertainty by that power. So I've now got 5%. I need to get that into an absolute uncertainty, so I multiply that 5% by what u squared is, which is 10.00 squared, or 100.0. So I can do that calculation, and I get 5.00 meters squared per square second. Now you'll notice the units of this absolute uncertainty are the same as the units of this absolute uncertainty. Well, that's really convenient because I'm adding them together. Did I say percentage? Absolute uncertainty. I can't remember what I said. The units of this absolute uncertainty and the units of this absolute uncertainty are the same, which is convenient because we're adding them together. I've either just repeated myself or I've corrected where I said something wrong. I won't edit it out. I'll leave it as it is. Right, so the absolute uncertainty in u squared plus 2as, that's just the absolute uncertainty in u squared plus the absolute uncertainty in 2as. So I'll take that number there, and I take that number there, and I add them together. And I get 5.45 meters squared per square second. But u squared plus 2as is all being square rooted. It's all being raised to the power of a half. So I need to know what the percentage uncertainty is. So I get the percentage uncertainty by doing this. It's a bit of a mess. Percentage uncertainty is going to be the absolute uncertainty divided by the mean value. I just chucked all the numbers in there to calculate the mean value. And I got a percentage uncertainty of 7.22%. Now, because we're raising that percentage uncertainty to the power, we're raising that quantity to the power of a half, we halve that percentage uncertainty. To get a percentage uncertainty in u squared plus 2as all to the power of a half equal to 3.61%. Well, that's V. That's the percentage uncertainty in V. So that means that the absolute uncertainty in V is just going to be the mean value of V, which we calculated right the way back here, multiplied by that percentage uncertainty. And that gives us this value here. Okay, this is good, except we need to do some rounding because we've got a 3 significant figure uncertainty. So we want a 2 significant figure uncertainty, and then finally we're going to round our mean value to the same number of decimal places so that we're not not got data that's not actually useful. And that's the answer. That's what V is. I'm not going to pretend that was easy. That is really, really tricky, and it needs a lot of practice. And you can get lots of practice using this QR code, scan it on the screen, go and have a look at the 𝗟𝗶ৃஹ questions. Hopefully the link still takes you to the right website, and you can have a go at doing those, and hopefully you'll do okay.